Okay, today we are gonna do a proposition which is called countable subadditivity of measure. Countable subadditivity. Okay, countable subadditivity of measures. Okay, so the proposition statement is the standard setting, let x as mu is a measure space and E1 we have a sequence of sets in sigma algebra, then measure of union of k is equal to 1 up to infinity ek is less than or equal to sum of k is equal to 1 up to infinity measure of ek. So it says that, so in the second property of the definition of measure, we have equality if we have pairwise countable pairwise disjoint sets. But this proposition says countable subadditivity, that no matter what kind of sequence of sets we have, disjoint or giant, like giant, then we have, this property will always hold this inequality. So if no matter if the sets are joint, but this property will always satisfy. So now we're gonna prove. The proof is kind of tricky, but it's based on the set theory setting. So we will construct that. Okay, let T1 is empty set, T2 I am considering that this is my E1, D3 is I'm considering that this is E1 union E2, and up to so on. So this means the dk is nothing but this is E1 union E2 union up to so on union ek minus 1. Okay, so this means that for all k is greater or equal to 2, because if k is 1 then my d1 is empty set. So now we are gonna see that if we take the, so then we say that, okay, so then we are able to see that sequence of set E1 difference D1, E2 difference D2, E3 difference D3 up to so on is a sequence of disjoint sets. So now this sequence is a sequence of disjoint sets, countable disjoint sets. Okay, sequence of disjoint set, and if we take the union of all those disjoint sets, this union is nothing but this is union k is equal to 1 up to infinity ek, and this is like, the proof is very easy. Take one element from the union of ek difference dk, and you will be able to see that it is nothing but it is actually union of, and the other way around. So I'm not going to do that, but how they are disjoint, so let's see. So suppose if we say that E1 difference D1, E2 difference D3, E3 difference D3, they are not disjoint. So if they are not disjoint, this means that they are joint. So to do that, so I'm gonna write, okay, how E1 difference D1, E2 difference D2 up to so on is a sequence of disjoint sets. Okay, so to see that we can say that, suppose let x belong to ek, we assume that, okay, the intersection is not disjoint. So we say that, okay, let x belong to, there is a element x dk intersection e, okay, m difference dm for, we assume that, okay, k is greater than m. So if we say that, okay, there is an element in the intersection of these two sets, then what does this mean? This means that then x belong to ek and x doesn't belong to dk, right? We can directly say that. So if x belong to, okay, x doesn't belong to dk, what does this mean? Dk is what? Dk is nothing but this is E1 union E2 union up to so on union ek minus 1. If something is not union, this means that it will not be in any of the sets. So this means that if since k is greater than m, so if it is not in any of these sets, so this means that then it implies that x doesn't belong to em. So if x doesn't belong to, then what does mean? Further it means, okay, x doesn't belong to em dm, which is a contradiction, since we saw that, okay, x also belong to em difference dm, but at the end we got, oh no, it doesn't belong. So this means that the sets e1 difference d1, e2 difference d2, e3 difference d3 up to so on, it is a sequence of disjoint sets. There's just the construction and we proved it. How it is disjoint and how the union is nothing but the union of ek. So now the proof is very easy because we got the disjoint set, so we can go ahead and use the second property. So the proof is very simple. Okay, so now the proof is, so measure of union of k is equal to 1 up to infinity ek. So this union is nothing but we saw that this union is ek difference dk. Now since ek difference each of them is the pairwise disjoint, so then by the second property this is nothing but this is sum of k is equal to 1 up to infinity measure of ek difference dk. Now but we need an inequality, so it is very obvious, you know, we need to use subadditivity, need to use monotonicity, which says that if a is subset of b, then measure of a is lesser or equal to measure of b. So since ek dk is contained in ek, so this means that then this measure of ek difference dk is less than or equal to measure of ek. So then this will be less than or equal to sum of k is equal to 1 up to infinity measure of ek, and we are done. That was the proof, nothing. We just use the second property because we need to come up with a sequence of disjoint sets, and somehow we came up, and then we saw that, okay, the sequence that we came up was a sequence of disjoint sets, and then if they were disjoint and the union was equal to the union of ek, then union of ek can be written as union of ek difference dk. And then since ek dk is a pairwise disjoint sequence, so then use the second property, which is sum of k is equal to 1 up to infinity mu of ek dk. But since ek dk is contained in ek, so this means they use the monotonicity, and by monotonicity we got this inequality. So this proposition, countable subadditivity, says that no matter if we have a sequence of disjoint set or not, this inequality will always hold, okay. And to make it equality, we need a sequence of disjoint sets. Thank you.